So thank you very much for coming to this talk. I know ZKML is kind of a hot topic right now. So hopefully everyone is keen on knowing more. I was trying to keep this presentation quite high level. I want to get a lot of use cases, get all of you in the audience to be excited about ZKML. And at the end of the presentation, then I would kind of talk about, like, if you're a developer, if you want to get involved, what should you do, or kind of like what's the next steps that everyone should be thinking about ZKML. So this is the rundown, as I've said just now. So the idea is, hopefully everyone already understands what ZKP is, or what zero knowledge proof can do. And when we say ZKML, we kind of assume that we already have a ZK circuit that can perform some kind of machine learning operations. So in this case, in my diagram, is a ZK circuit that can perform neural network. So NN stands for neural network. Right? So a lot of the models that we know, stable diffusion, large language models, they are all neural networks. So let's say we already have a ZK circuit that can perform that. Then naturally, there are three types of data that go in and out of this circuit. Right? So for input on the left, we have some input data. For stable diffusion, the input data would be the prompt. Right? An example prompt is something like, oh, I want to generate an image of an astronaut riding a horse. Right? So that's my input data. For a face recognition model, the input data would be the image of my face. And then the other type of data that goes into our circuit is model weights. Right? So nowadays, if you open source models, model weights is public. For OpenAI, for instance, the model weights are private. We kind of know how the model works, but we don't really have enough data to know exactly how it works. And then the output. Right? So again, the output depends on the use case. If it's a facial recognition model, the output could be an encoding of my face, right? Like a hash or an ID. For some kind of, for stable diffusion models, the output is an image, right? So it all depends. But that's how, in general, a ZKML design would look like. So from here, there are actually three types of use case we can talk about. So first use case is actually the use case where we want to keep our input data private, but our model weights public. Right? So the way to think about it is there is this model that is completely public, open source, that everyone can trust. Right? So a model that has very good performance that everyone can trust, so that when we put in some private data and we get a result, people can trust that result as being reliable. Right, so to put it in a more concrete use case, let's look at this example. So at authentication, right? So a use case with private input data and public model would be authentication. And authentication that uses your biometric data, right? So it could be, say, a smart contract wallet with biometric authentication, right? Then your model would be either something that can encode your fingerprint very nicely, right? Securely, collision resistant. If we have such a machine learning model, which actually we do, right? We have used actually a lot of different machine learning models for fingerprint recognition for a long time. Well, then if we can kind of write that model in a zero knowledge circuit, then we can use that for smart contract wallet authentication. Well, of course, there is a lot more kind of complications and kind of implied things that you need to take care, right? Such as you don't want people to be using the same scan twice. So you probably have to check for that. But that's kind of the essence of it. Right? Another thing is probably you can use your face and any other kind of biometric data. The other use case I could think of for kind of the case for private input data and public model is proof of humanity. Right? So if any one of you have done the, I think, Git passport proof of humanity, you know that you have to submit an image. And that image is not private because when the machine determines that you're not a human, that image of you actually gets sent to some human, a committee, a court, to determine whether this person is actually human or not. But let's say if we have a machine learning model that can identify whether this image is a real person versus, I don't know, an AI-generated person. Well, then maybe there is a way that we can have a proof of humanity without actually sending our picture off to some server or to some service provider. Right, so that's kind of like the use case for the first type of use cases for ZKML. The second type of use cases is the flip side of the first type. Right, so we have the option to keep our input signals private or public. So now let's switch. What if we have private model weights, but public input data? And the use case of this is you can think of it as more commercially. Actually, a lot of Web 2 companies probably are not willing to share the model. Right? So, for example, OpenAI has publicly said that they're not open sourcing their models because of a lot of different ethical concerns, security concerns. So this use case could actually be helpful to bring Web 2 models or Web 2 use case onto the blockchain. Right? People tend to think that the blockchain has to be all transparent, but in this case, if we can at least keep the model weights private, which is, model weights private, which is the kind of the most expensive part of a machine learning training process, then there is also a tons of use case for that. So for example, a way you can think of it is we can have a ZK version of Kaggle. So for those of you who don't know what Kaggle is actually a bounty platform such that companies can post their hard problems onto these platforms and request for submissions from the public to basically solve that problem, right? So it could be classification problem, then the metric would be accuracy. It could be a generative problem, then accuracy is something else. But the idea is there's a bunch of people in the public competing to submit their model, their best model for a particular problem. The problem with this is that actually, in order to allow this platform to evaluate whether your model is really that good, you have to submit your source code, right? So of course you can say that, well, there's legal license, like your source code is kept safe unless you really like win the thing. But essentially, we're still giving up our source code to this platform. So imagine in a case where we have ZKML, then there could be a way that we can share our model, well, not share our model, a way to prove our model performance without sharing the model. Right? So for example, I have a data set of 1,000 samples. I will just run through this 1,000 samples with my model, construct the ZK proof, and submit the proof. Right? And by submitting the proof, I'm showing you that my model is 99% accurate. Okay? And that's probably good enough for a competition. Right? And only after I win this competition, then I will decrypt the model for you or actually share the model weights with you. So this is a way where could be private model transaction. Like how can I sell a private model to someone reliably? How can the other person trust that this model is actually as performant as they say? So this is one way to do so. And together with some design of smart contracts, you can actually also guarantee like whether this whole transaction is fair to both sides of the buyer and the seller. And the third type of use case is actually kind of counterintuitive. So a lot of people think about ZK as being privacy related. And this, actually, I added this slide probably within the last month or so to my presentation, because I think there's actually a lot of potential to just make everything public. So you might think that, well, why would I want to make things public? you use ZK for privacy, right? Especially ZKML. I probably want to keep my personal data private, or as a company, I want to keep my model private. So why would I want everything to be public? Well, we want it to for compression purpose, right? So succinctness. If we keep everything public, there's still a use case or usefulness to it because we know that currently, at least on EVM, it's impossible to put the full machine learning model inside a smart contract, right? It's limited by contract size. It's also limited by the operations that you can actually perform inside a smart contract. But if we have this in ZKML, then essentially what we can do is we can take all the computation, all the machine learning operation off-chain, right? We do everything off-chain. We have a huge server. They crunch the numbers, compute the ZK proof, and only with the very small size proof, we submit it on-chain. And that could be useful for quite some purpose. So one of the case you can think of is algo trading, right? Let's say if you have an investment DAO that wants to use some kind of algorithm to make investment decisions or actions, right? How can I prove that this is actually based on my algorithm other than someone just randomly submitting actions onto the chain? This could be one use case. The other use case, or the other application for this particular type of use case is a new kind of idea, which is AIGC NFT. So AIGC NFT is not a new thing. A lot of our NFTs nowadays are actually already algorithmically or AI generated. But there's a way, there's always a talk about, well, how do I prove that this image is actually generated by this person or by this model, right? Let's say I put in a prompt into Stable Diffusion. How do I prove that I actually did that action? Not that I just downloaded a random image off the internet and minted it as an NFT. And this is actually a newly submitted EIP. If anyone wants to, go check it out. So the number is 7007. The idea is that, well, what if we can then prove the process of this AI-generated content, right? So AIGC. So let's say I have an image that I generated from the prompt, an astronaut riding a horse, right? This whole and then I get an image, right? Nowadays, if you want to do an AIGC NFT, you will probably just mint that image as an NFT. But ZKML essentially can prove this whole process, right? So I can prove this process that I actually turn this prompt into this image via this particular model. And this actually allows us to do two things. First of all, is verifiable creatorship, right? So it proves that I am the person who created this image, right? So it will solve quite a lot of IP, arguments of whether the person actually was the creator of this image. And the other thing is it actually creates a new concept of what it means for AIGC collection. So in this case, one particular version of a model, right? So let's say, I don't know, Stable Diffusion 1.4 with a particular seed number. That particular model would be a NFT collection, right? Because with a fixed model, one prompt can only give out a particular image, right? So that gives you a quite kind of deterministic way of determining, AIGC, NFT ownership, and creatorship. So if anyone wants to check it out, it's still in the pull requests of the EIP repository. And this is kind of the whole process. I'm not going to really go through it too deeply, but the idea is you can think of it as if you are a user who wants to make use of this particular model that some service provider provide, essentially what you would do is I will propose a prompt. Right? I would say that I want to generate an image with 100 people in Serbia, right, in front of the MTS theater. Right? And then this prompt would go into the model, and also there will be a prover that generates the proof. And then so now you don't just need the image to mint this NFT. You also need the prompt, along with the proof and the image, or in any other form of media that your AI model, your machine learning model generates to. Right? And this generation process is verified by a CK verifier contract, and then you mint it as an NFT. So this is like the third class of use case, and it's also the most immediately available use case, as if we are willing to make everything public, there's actually a lot kind of, I guess the proof size that we're talking about is actually quite small, and well, basically you get a lot more benefit if you're willing to keep everything public and just want to use CK proof as compression or as succinctness. Right, so now we're going to dive in a little bit into history before we talk about the outlook. So just want to kind of present to you that we're still at a very early stage of ZKML. And for those of you who would like to get involved, there are two main problems that researchers or developers are dealing with most of the time. So the first thing is CK proof is in fixed point arithmetic or modular arithmetic. And typically, machine learning is in floating point. All right, so we are actually gaining advantage of like gradient boost and stuff from the floating point weights. So there is this quantization problem that we need to solve, right? How do we turn something that is in floating point in machine learning into fixed point or modular into CKP? And the other problem we encounter is also that we are not getting a lot of size or depth in our machine learning models currently that we can fit into ZK. So just a quick kind of run through. Actually, the term ZKML started 2 years ago, so not very long ago. And the first example was actually just linear regression. So linear regression means that you just have a sample of data, you determine the best separation of your data, right, and then split them into class 1 and class 0. And then we started thinking, well, why can't we put neural network into CK? Maybe we can do that, right? So then people started putting it first, maybe just the final layer, and then eventually the full convolution network. So that's my repository. And then we kind of run very quickly in the last few months or so. So first of all, in ETH San Francisco, the same group that coined the term ZKML also did a proof of concept of AIGC as NFTs. And then we also get a lot of performance boost as well. So there are two very important ongoing projects that you would absolutely like to check out if you're interested in this field. So C-Conduit's ECKL and also Daniel Kang's ZKML repository. So those two are making use of the Rust language and the Halo 2 prover to gain a lot of performance boost and fit like much larger and much deeper model into a CK proof. So the latest updates, at least as far as I remember, is that Daniel's group has already been able to get GPT-2 into CKP. Of course, when we say we got GPT-2 into CK proof, we're talking about using a very, very powerful machine with a lot of memory, right? So it's not like you can do it on your laptop. But at least there's already attempts that you can do it, and it's on some, I guess, consumer-grade available cloud machine. Right, so, well, the reason why I want to talk about history is because I want to tell you then what's next, right? Okay, let's say we're already given all the history just now. We already have some ways that we know how to make big models available in CKP. Well, what are the immediate next steps? So the first thing is actually there are the projects that I've mentioned is pretty much it. So that's all the projects in the ZKML field. So it's exciting, but at the same time, it's a little bit sad because we do need many more projects into this field. So if you don't have to be a CKP engineer to get started. Actually, if you have some machine learning background, some AI background, that's even better. And there are quite some open source libraries that you can contribute to. I've listed 2 of my own. So that's a machine learning library in Circum, and also a library that transpiled from like TensorFlow Clara's model into Circum, the CKP language. And the idea is, well, why do we need contribution? The way I think about it is that we have, well, think about the team that builds TensorFlow or PyTorch, right? Think about how many people they have. Think about how many types of operations they actually support. Essentially, for all these libraries, we have to transform every single of those operations into some kind of a template in ZK, right? So that is not, the size of the work that needs to be done is not something that can be covered by just a few teams and me personally. So we actually need a lot of people who are excited, who knows machine learning, or even just linear algebra, to contribute to like just moving or migrating all the machine learning operations into ZK. The other thing is actually use cases, right? Not just build use cases, but brainstorm use cases, right? So one of the biggest problems we have right now is that, well, we all know this is a very important thing, right? That's why you have been hearing about ZKML everywhere, but we don't know what it is good for, right? Or at least we know a lot of moonshot applications or moonshot ideas, but we don't know what we can build right now, right? And with this AIGC NFT idea, that is probably one of the most tangible use case right now. And I'm definitely personally looking for someone to build the first kind of use case. I mean, I could build a model myself, but I don't really have a use case to issue my own NFT collection at this point, right? So actually, some of the projects told me that I actually want to issue a collection for my users, and maybe AI-generated art could be a good thing. And if you want to build something like that, feel free to reach out. And I think this could be a very cool kind of like immediate thing that people know that, oh, ZKML is actually useful. And the other thing is there's also another class of tangible use case right now, which is gaming. In particular, there's a game that is built by Modulus Lab called Leela versus the World. You can just search it, and that's probably the first result you're going to get from Google. And this game is interesting because it kind of simplifies how we can use ZKML and build a very interesting and fun use case. So the idea is they have this offline bot that can play chess very well, right? And this AI, and there's also the other side of the player is the user, so the world. So everyone can submit a action or a step to play against this bot, right? And the reason we know that it's a bot, not another person on the other side behind the screen playing against you, is because of ZKML, right? So I actually can reliably know that I am playing against something that is controlled by a particular model, right? And that's what makes it interesting, because you know that you are actually playing against some kind of quite good performing model, and you're trying to beat the model, right? So human versus AI, essentially. So that's also a very tangible use case. It's already on-chain online. And this doesn't limit to chess. We can do it with a lot of different games. It's just a very fun way so that people can notice ZKML. So with that, I'm going to close up my presentation and welcome any questions. I really hope that there are more people who can get involved in ZKML. Building applications, you don't need to be a ZK circuit engineer. There's always a lot of toolings and libraries to help you to build that use case. Thank you. So I'm guessing it's question time now. Is there any question? I can't really see. There's a question there.
So you mentioned how when there's a private model and public data sort of thing, right? You can prove that something was generated by a model. But are there any ways to sort of fake that, you know, to make something seem like it was generated by a model to pass a proof, but not really be generated by the model?
So according, if it's I guess a sound ZKP, it shouldn't really happen. I think it's also a good time, thanks for the question, it's also a good time to clarify a bit. So at least right now, this circuit in the middle, the structure of itself is not private, okay? So actually you can see the model architecture. The only thing you can hide is the weight, okay? So that's already a lot of kind of constraint or limitation to it. So at least you know that this is the structure of the model and all the computation. Actually, the computation that's being done is public. Of course, in the future, we're also talking about, like, what if we use a commitment of the function or of the circuit instead of the circuit itself, right? So that we can also hide the model. But to answer back to your question, so if it's a sound ZK proof, it shouldn't be able to forge it. Of course, currently, there is still a lot of different little bugs in a lot of different proving systems. But like once those are fixed, like if it's a sound and complete CKP, it shouldn't be able to forge like that proof.
Does that answer the question?
Yeah, it does. And these are non-interactive proofs in that case.
Yeah. So all the proofs that I've mentioned here are non-interactive. So we are just submitting like a single proof with a on-chain verifier to be able to say that this proof is true versus this proof is false.
That's really wild, yeah. Thanks.
Do we have any more questions? Yes.
Yeah, thank you. I have a follow-up question. Is there any way to establish maybe quality of this model without like revealing all model weights? For instance, if I train the model using like entire validation set and like without training data, so I like focused only on validation set, trained my model, it perfectly worked, but it doesn't work anywhere else. So like, yeah, beyond this validation set.
Right. So the way you can do it, that's actually a very good question as well. So it's the same use case the same type of use case we're talking about here, right? The question is, well, if you give them a testing or validation data set, they can essentially train their model on this set and perform very well, right? So the way you can actually avoid that is after someone say that, okay, I'm done training the model, you ask them instead, the model weights is still private, but you ask them to hash the model weights, right? So it's the good old commit review scheme, right? So you ask them to hash the model weights and make that a commitment, either on the smart contract or just publicly broadcast it. And then you send them a testing data set, right? So then whatever proof that they make the new proof, it still has to come out as the same model weight hash. So you know that they haven't changed the model weights just to get better performance on this new data set that you give them.
Does that answer your question? So we have time for one more question. Are you raising a hand? Oh, microphone, please.
That's okay. The question sounds so silly, I'm kind of afraid asking it. Couldn't I build all these ideas by just having the model sign the result instead of doing all the dance with the zero knowledge proof? So what does the proof give me that its simple signature over the result doesn't?
So I'm not sure if I understand fully. So by signing, you're probably just saying that like this is a result that's given by me, right? Like, so for example, I think I understand the question. So let's say, well, so the thing is, if you can't prove that it comes from a machine learning model, essentially, if you give me a data set, I can manually, like let's say if it's image, I can manually just look at it and be like, okay, this is a dog, this is a cat, this is a rabbit, right? And I can actually submit that that result online, on chain, and get 100% accuracy, but that doesn't make the result useful. Of course, if you just want someone to do that particular task, right, then that's perfect. But if you want to somehow have this model to, maybe your company has some other use case that you want to use this model for, right, then you probably need this model and probably need to, before you pay for it, get a proof that it is a useful machine learning model, that I can use it in the future, I guess, if that answers your question.
I think so. Thanks.
No, if you want to clarify your question further on, feel free to do so.
No, I don't want to embarrass myself any further.
So we are out of time, but if anyone wants to, of course, if Cathie is open for another question, I think we can pull it off. So if there's any more questions, feel free to raise a hand, and if not, yes.
Hi, just a short one. In the case of these models, how big are the execution trace matrices? Just the order of magnitude, if you have it.
I'm guessing by execution trace, you're talking about like prover time or prover computation intensity.
Yeah.
So for GPT-2, I believe, I'm not the team that does it, but from the team that does it, they're saying that you need a machine with in the order of like tens of terabytes of RAM.
Okay.
In order to perform the whole like proof trace of this GPT-2 model. So that's the order of magnitude we're talking about, at least for now.
Okay. Thank you very much.
So we're gonna, I first of all want to thank Cathie for an amazing talk, and I want to thank everyone for engaging with your questions. So can we please get an applause for Cathie?